Welcome back to Science Multinizers. Welcome back to our channel. Today we are going to see tutorials on photoelectric effect, and these tutorial questions are typical GC questions, that is from the Cameroon General Certificate of Education Board. So let's begin with the problem statements. Figure 1 shows a graph of stopping potential V plotted against frequency for a certain metal Z. Roman 1. Calculate the threshold frequency and wavelength of the metal, given that the work function is 3.8 electron volts. Roman 2. To which region of the electromagnetic spectrum does the wavelength calculated in Roman 1 belong? Roman 3. Of what significance is the gradient of the graph in the figure 1? Draw a setup from which the results above will be obtained. That's June 2012 question number 2. And that is the figure, that's the shape of the graph that was given, in which we have the stopping potential V against the frequency in Hertz. Okay, the next question is June 2013 question number 9. A says define stopping potential. B, use Einstein's photoelectric equation to explain Roman 1 why for a particular metal electrons are emitted only when the frequency of the incident radiation is greater than a certain value. Roman 3, why the maximum speed of emitted electrons is independent of the intensity of the incident radiation. C, the figure below shows how the frequency f of incident radiation on the metal surface varies with the energy of the emitted photoelectrons. From the graph, Roman 1, determine the threshold frequency and calculate the maximum wavelength of the emitted electrons. Roman 2, calculate the values for the Planck's constant and the work function. And D, an X-ray photon has wavelength of P times 10 to the negative 10 meters. Calculate the values for A. Roman 1, the momentum. Roman 2, the energy. Roman 3, the mass of the particle associated with the photon, which moves at the speed of light. So those are the problem situations, and this is the graph representing this particular problem. That's the A section. And so let's get the proposed solution. We are going to begin with the very first question. Figure 1 shows a graph of stopping potential V plotted against frequency for a certain metal Z. Calculate the threshold frequency of the metal, given that the work function is 3.8 electron volts. Now, the work function phi is equal to hf naught. This means that the threshold frequency will be the work function divided by the Planck's constant. And so f naught will be numerical application. We give the work function is 3.8 electron volts, that's it there, and since it is in electron volts, 1 electron volt, we saw in the previous video that 1 electron volt is 1.6 times 10 to the negative 19 joules. So you multiply by that conversion factor and we divide by the Planck's constant, and the result gives us 9.184 times 10 to the power 14 hertz. And so we can also calculate the wavelength. The wavelength, we know that lambda 0 will be equal to frequency. Since we know that the speed is equal to the frequency times lambda, it definitely means that lambda 0 will be c divided by the frequency. So if we take the speed of light, which is 3.0 times 10 to the power 8, and we divide by the frequency, we get 3.0 times 10 to the power 8 divided by this approximated value of the frequency, 9.184 times 10 to the power 14. It's going to give us the value of the threshold wavelength. So that's 3.0 times 10 raised to the power 8 divided by 9.184 times 10 raised to the 14. So it gives me approximately 3.27 times 10 to the negative 7. So it's about 3.27 times 10 to the negative 7 meters, which is an approximation of 327 nanometers. And this wavelength range falls in the range of UV, that's ultraviolet. Likewise for this frequency. Okay, so the next question says, to which region of the electromagnetic spectrum does the wavelength calculated in Roman 1 belong? So we saw it belongs to the ultraviolet, so it's ultraviolet light because it falls in the range of the UV. Okay, of what significance is the gradient of the graph in figure 1, and draw a setup for which the results above could be obtained. Okay, so from there we are going to write down the general equation which governs this particular problem when um, light of sufficient frequency strikes the surface of a metal. So for a better understanding, again, you can click on the video link just at the description of this video, that is the previous video. Okay, so we saw that the energy which is supplied is equal to the work function plus the maximum kinetic energy, which is also equal to E times the stopping potential. And from here we see that if we make the stopping potential the subject, the stopping potential Vs will be equal to H on EF minus H on EF naught. So it is in the form Y equal to mx plus C, and HE on HEF naught will give us the work function. So the gradient, the significance of the gradient is simply the Planck's constant per unit charge. But what does H on E mean? The ratio H on E indicates the amount of energy carried by each individual electron as a result of the interaction with a single photon. So that's the meaning. So H on E is not just the Planck's constant, but it is the Planck's constant divided by the electronic charge. Now the next part says draw a setup from which the result above could be obtained. So what they are asking is simply the setup which you can draw in order for us to determine the stopping potential. So we can have metal surface. So this can represent my metal surface. Let me put it. That can be my metal surface. And on this metal surface, I'm going to connect a battery. And then beside I can connect a metal. I am metal. And I close. So that's the circuit. Now up here we can show that light of sufficient frequency is falling. And this has electrons which are being ejected. So that's actually the setup. This is an metal. Okay, so that's it about that question. Let's move to the next. The next question says, what is stopping potential? And use Einstein's photoelectric equation to explain why, for a particular metal, photoelectrons are emitted only when the frequency of the incident radiation is greater than at a certain value. So we begin by seeing that stopping potential is the minimum negative voltage applied to the anode to stop photocurrent. Now, for the case of Roman 1, we want to show that for a particular metal, electrons are emitted only when the frequency of the incident radiation is greater than a certain value. That value is actually known as the threshold frequency F0. So we are going to do that. So we have, if I have a metal surface, say like this, which is illuminated by a source of light, that's an electromagnetic radiation. Now this has a certain source E, and this energy has to overcome the work function, and definitely when electrons are ejected, they gain kinetic energy, Ke. Now, so that energy, E, is given by the energy to overcome the work function plus E max. So that's the kinetic energy maximum. Now, what does this imply? This means that the maximum kinetic energy, Ke max, is equal to E, which is the energy of the source, which is given by Hf minus Hf naught. But this maximum kinetic energy, Ke max, is always positive, greater than or equal to 0. We are going to take that case. Now, since it is always greater than or equal to 0, this implies that Hf minus Hf0 should always be greater than or equal to 0. So this means that Hf should be greater than or equal to Hf0. And so the H's can simplify, which means that my F should be greater than or equal to F0. So what does this imply? We show that why is it that for a particular metal, electrons are emitted only when the frequency of the incident radiation is greater than a certain value. So this is it. This is how we can derive that from Einstein's photoelectric equation. And we see that the value of the frequency in which the frequency of our radiation should be greater than is the threshold frequency. And that is one of the conditions we saw in the previous videos for electrons to be ejected from the surface of a metal. The frequency of the incident radiation, that's our source F, should be greater than or equal to the threshold frequency. When it is equal to the threshold frequency, the energy will simply be equal to the work function. And so electrons will just be excited, but they are not going to gain kinetic energy. So that is how we can explain that fact using this concept. Okay, so let's pass to the next question. Okay, so for the next, we have now we are supposed to show that, or the next one says the question is actually omitted because they also said that we should show that the maximum speed, that was a Roman 2, the maximum speed is independent on the intensity of the radiation. So before passing to the graph, let us verify that. Now, as we are just from seeing, we saw that the maximum kinetic energy, Ke max, is equal to Hf minus Hf0. But the maximum kinetic energy will be equal to a half V max square, which is equal to Hf minus Hf0. So if you make V max the subject, V max will be equal to the square root of 2 times Hf minus Hf0. All of this divided by the mass. Now we see that the maximum speed is only dependent on the frequency and not on the intensity. And the intensity I is the power radiated per unit area. And so the maximum speed clearly does not depend on the intensity, but rather depends on the frequency. So that's how we can explain that particular concept using the Einstein's photoelectric equation. Now the C part says the figure below shows how the frequency F of incident radiation on the metal varies with the energy emitted of the emitted photoelectrons. Okay. From the graph, determine the threshold frequency and calculate the maximum wavelength of the emitted electrons. Roman 2. Calculate the value for the Planck constant and the work function. So that is the graph. Now to determine the threshold frequency, F0. F0 is the minimal frequency, the smallest of the frequencies which we need for photoelectricity to occur, for photoelectric effect to occur. So we are supposed to read that value from the graph. So checking the graph, we see that at a certain point we have like an intercept. So the graph meets the y-axis at a certain point, and so that is the point where um, we are supposed to deduce the value of the threshold frequency. And so when we look at it keenly, the point is here where the graph cuts. So that is the smallest of the frequencies that can be observed at that on that graph. So if you check it clearly, it is going to be at about, we have 3, and in between 3 and 4 there are 10 gaps. So it means one of those small boxes should be 3.1. So we can observe 3.1, 3.2, 3.3, 3.4. So this should be about this 3. It should be 3.1, 3.2, 3.3. It should be 3.4. So that's 3.4. But remember, the frequency above is given times 10 to the power 14 hertz. So we can deduce from the graph that the threshold frequency is equal to, that's Roman 1. The threshold frequency is 3.4 times 10 raised to the power 14 hertz. Okay, now the next is we should calculate the maximum wavelength for the emitted photoelectrons. Now, since the frequency f0 is that's the minimal of the frequency, it means the maximum wavelength is going to occur for this value of the frequency. So we can calculate the maximum wavelength simply using the notion that f0, that the speed of light will be equal to f0 times lambda 0, in which is lambda 0 is our maximum wavelength. So this implies lambda max will be equal to c divided by f0, and c is 3 times 10 raised to the power 8 divided by f0, which is 3.4 times 10 to the power 14. So this gives we have 3 times 10 raised to the 8 divided by 3.4 times 10 raised to the power 14. So it gives us 8.82 times 10 to the negative 7. So it's an approximation of 882 nanometers. So that's the maximum wavelength that we can get. Now Roman 2 says calculate the values for the Planck's constant and the work function. Okay. Now so let's calculate the values for the Planck's constant and the work function. Now we see that we have a graph of F against E max in electron volts, but we saw that E is equal to the work function W naught plus E max, which is the maximum. So this means that E max will be equal to HF minus HF0. So if you make F the subject, no need to make E max the subject since it's frequency against E max. So make this means E, which is HF, will be equal to the work function, which is HF0 plus E max. Now this means that my F will be equal to E max divided by H plus F0. So we clearly see from here that F0 is the intercept, so that's it there that we saw above. Now E max divided by H, so this can be written in the form 1 all over H times E max plus F0. So we see that the gradient of that graph is the reciprocal of the gradient M is the reciprocal of the Planck's constant. So let's calculate that gradient. So M will be the variation in F divided by the variation in V, and that will be equal to, so we are going to look for a point, or we are going to look for points which we can easily use. If if we take the point, for example, the point 4, and we link it with the points at the let's look at it keenly. So here we have point 4. So we can take our triangle like this point. So we'll read this value down here. We'll read this value. We'll read this value. Then we are also going to take, let's use say this point, or let's not just take direct points, let's use any point. Okay, we can use this point for example. This point for example, but it's not too clear. So we are going to realize this is 9.1, 9.2, 9.3, about 9.4. So that's 9.4 here. And here we have this 0 right up to 1. So one of these boxes should represent 0 0.2, 0 0.4, 0 0.6, 0 0.81. So here we are just at 0 0.2, and then since we took this at this point, we follow this line down, so here will be 2.2. So it's in electron volts, and here is a 0.4. So using that, we can calculate the value, the gradient. So the gradient will be 9.4 minus 4. Let's not forget the multiplication factor, times 10 raised to the power 14. All of this divided by the variation in E. So that's 2.2 minus 0.2. All of these times, I want to put it times in joules, times 1.6 times 10 raised to the negative 19. Okay, so let's do the numerical application. So we have 9.4 minus 4 times 10 raised to the power 14 divided by 2 times 1.6 times 10 raised to the negative 19. It gives us a value. It gives us 1.687 times 10 to the power 33. This is hertz, that's per second, and what is down is the joules, so it's per joules per second. Okay, so this means for us to get the Planck's constant, h will simply be equal to 1 divided by the gradient, that's the slope m. So this means that h will be 1 divided by 1.687 times 10 to the 33, which will be equal to it gives us about 5.92. So it gives us 5.926 times 10 to the negative 34. So I'm going to approximate this to 6.0 times 10 to the negative 34. Okay, so the actual value of the Planck's constant is 6.62 times 10 to the negative 34. So the reason why this can be a little bit far is also due to the clarity of the graph, so that the little errors that can be committed due to the clarity of the graph and the how precise we are at the level of collecting our values. So we see that the graph, the initial graph that was provided by the board, this was not really clear from the source which I had the question, and so it becomes a little bit cumbersome for us to get the right readings and so on and so forth. So this is just an approximation. So you can also try it on your own site and you can comment the values of the Planck's constant, but it should be very close to our value because this is a little bit too far. Okay, so we are going to proceed now to get the work function. So what is the work function? The work function will simply be the Planck's constant times F0. Okay, okay. So now we have deduced the value of the Planck's constant and now we have to get the value of the work function. So the Planck's constant gives us approximately 6.0 times 10 to the negative 34 joules second. Now with the work function W0 is simply HF0, which is 6.0 times 10 to the negative 34 times the frequency, which was the threshold frequency, which was 3.4 times 10 to the power 14 hertz. So we punch that to get the work function, and we are going to leave our answer in electron volts. So that will be 6 times 3.4. That will be times 10 20. So it gives us 2.04. 2.04 times 10 to the negative 19 joules, and this is equal to 2 point in electron volts. We are going to divide that by 1.6 times 10 to the negative 19. So if I take that by 1.6, it gives me 1.275 electron volts. So that's the work function of our the metal. Okay, so now we are passing to the D part of the question. The X-ray photon has a wavelength of 3.0 times 10 to the power negative 10 meters. Calculate the values of A, the momentum, Roman 2, the energy. So to begin, Roman 1, we are looking for the momentum P. The momentum P. Now we can use the fact that since it is this energy is quantized, so we can use lambda is equal to h divided by p, where lambda is the Broglie's wavelength, so it means that p will simply be h divided by lambda. So this will be equal to 6.62 times 10 to the negative 34, all of this divided by the wavelength 3.0 times 10 raised to the negative 10. Okay, so it gives us times 10 raised to negative 20. So it's 2.21. So the momentum will be equal to 2.21 times 10 to the negative 20 kilogram meters per second. Roman 2. The energy E will simply be given by Hc divided by lambda, which is 6.62 times 10 to the negative 34 times 3.0 times 10 to the 8, all of this divided by lambda, which is 3.0 times 10 to the negative 10. So the 3 will simplify and we have 6.6. Negative 34 plus 8 will give us negative 26 plus 10, 16. So it's going to give us the energy will be equal to 6.62 times 10 to the negative 16 joules, in which we can also convert it to electron volts. That's we divide it by 1.6. That's 6.62 times 10 raised to the negative 16 divided by 1.6 times 10 raised to the negative 19. It gives us 4137.5 electron volts. So that's it about the energy. Now let's see the last part of the question. Okay, so now we have to calculate the mass of the particle associated with the photon, which moves at the speed of light. Now we know that the momentum is the mass times the velocity of the of an object. So this means that the mass will simply be the momentum divided by the speed, and the momentum was 2.21 times 10 to the negative 20. That's 2.21 times 10 to the negative 20 divided by 3.0 times 10 to the power 8. So the power 8. So it gives me about 7.37 times 10 to the negative 29 kilogram. And so that is the mass of the particle associated with the photon, which moves at the speed of light. And this brings us to the end of this tutorial video. If you have any question, you can drop it in the comment section, and please do not forget to like, share and subscribe. Thanks for watching.